we're going to take a look at another integration technique that may help us integrate some problems that have a unique feature to them. To do this, as you see I already have over there on the right, we're going to be using our Pythagorean identities to basically turn two terms into one term. Because notice like here, we can turn two pieces into one piece, or two pieces into one piece. And of course we can manipulate those to get the kind of the thing that we need. So here's the idea. Let's say that we were given this integral. Now, this integral you should actually already know how to do, because this is just the arc sine, the definition of our arc sine. But if we didn't know how to do that, how would we approach this problem? Well, here's the kind of key that gives it away from you. Anytime you see a number and a function squared kind of in this kind of orientation, you're thinking maybe a trig substitution will work, especially when that number and that function being squared is in some type of radical or some type of power. This generally works. Now, this is somewhat of a backward substitution of what we're used to doing. Normally we're used to doing letting a letter equal some function of x. We're actually going to kind of do that backwards this time. This time we're going to let a trig function equal the function, which is x most of the time up here, in our equation to fit one of our trig identities. So if I take a look at this one of our identities, I need to manipulate these till I can get 1 minus a function squared, because that's what I have here, 1 minus a function squared. You notice if I take the top one, I can manipulate that to get either sine squared theta is equal to 1 minus cosine squared theta, or I can manipulate that and get cosine squared equals 1 minus sine squared. Actually, it doesn't matter which way that you do it. Let's go ahead and leave it like that. So since that's the thing being squared, I'm going to say let's let the sine of theta equal to x. Now we're still doing a substitution, which means I want to replace all the x stuff with theta stuff now. So just like always, once we do a substitution, take the derivative. The derivative of the left-hand side is going to be cosine theta d theta, and the derivative of the right is just dx. So now we can substitute. This becomes the integral of dx is just cosine theta d theta over the square root of 1 minus sine squared theta. Right, I just replaced the x with sine. Now here's the entire reason that this trig substitution works. Because now I can write these two terms under this radical as one term. So this is the integral of cosine theta over the square root of cosine squared theta using my Pythagorean identity. All right, so now this is where it gets a little bit technical, but not too bad. Anytime we do the square root of something squared, technically it is the absolute value. So here we have the cosine of theta over the absolute value of the cosine of theta d theta. Well, that would actually be a fairly tricky integral to do. We'd have to do it in a piecewise function kind of thing. Or we can cheat a little bit and just kind of restrict the bounds on this function. Let's say I wanted it to always be positive, because if I know that the cosine of theta is greater than or equal to 0, then I could get rid of the absolute value. Well, if you think about way back of our trig stuff, or all students take calculus, I can see that cosine is positive in the first and fourth quadrant. So if I were to say, do this, let's call that negative pi over 2 down here and positive pi over 2 up here. If I were to say, let's restrict our angle to only be from negative pi over 2 to positive pi over 2, then I know that cosine here would be positive. So I'm going to go ahead and say, let's let our angle fall between, now it can't be that because it'd be 0, it may be divided by 0. So that's what I'm going to do. So since I've restricted my angle, I now know that the cosine is positive, so I get the cosine of theta over the cosine of theta d theta, which turns into an extremely simple integral here. Well, the integral of theta, or d theta, is just theta plus c. Now actually, here's where it gets a little bit tricky, because our answer is going to be in terms of thetas, but our original integral was in terms of x's, so we got to get back. Now this is actually the easiest case scenario. Remember, we're always going to go back to our original substitution to help us out. Can I figure out what theta is? Well, this is just a trig equation. If we take the arc sine of both sides here, we can see that theta is the arc sine of x plus c from this line right here. So if you're wondering, from here is how we got that. Just did the arc sine of both sides. And there we go. But we knew that that was the answer before because that's one of our known integrals. But you can kind of see now that you can actually work out that that integral is actually the arc sine. So let's take a look at another one where we just don't actually know what the answer is and see how this works out. Let's do a weird power one. Let's see if I have the integral 1 over x squared plus 4, let's do the 3/2 power dx. You would always go through all the same questions you normally would. Can I integrate it directly? Can I do a substitution? Can you do by parts? All those questions generally come into play. But here I'm seeing I have two pieces raised to a weird power. One is a function and the other is a number. So I'm thinking maybe this trig substitution thing will work. Now we're going to do a couple steps of algebra to get us into a situation. The two trig identities that we're always going to use, these two, both have ones where the number is. But here our number is a 4. So I'm going to do just a couple of steps of arithmetic, or algebra if you want to call it that, to make it so it's a little bit easier to see which trig identity it fits. Here I'm going to factor a 4 out of both of these, so that's going to give me x squared over 4 plus 1 to the 3/2. Now these two things are joined by multiplication, so that's going to be, I'm going to rewrite two things here, that's 4 to the 3/2. I'm going to write that as x over 2 squared plus 1 to the 3/2. Now the reason I wrote that as one thing being squared is because I need to replace it with one of my trig functions, so I want the whole thing as a squared quantity. Well, 4 to the 3/2 power, remember that's a fractional exponent, is telling you to do two things, a power and a root. So the square root of 4 is 2 to the 3rd is 8. So I'm going to just go ahead and say this is 1/8 integral 1 over x over 2 squared plus 1 to the 3/2 power. All right, by looking at this, now we're going to try to fit one of our trig identities over here. So I'm looking for a function squared plus 1. Well, the second one up here is exactly already in that form, right? We have a function squared plus 1. So our substitution here, we're going to say, let's let the tangent of theta be equal to x over 2, right? Because that's the thing being squared. Now we're also going to have to replace everything else, so I know I'm going to have to replace the dx, so we're going to take the derivative of this. Most of the time, not always, but most of the time it's helpful if you just go ahead and get the x alone all by itself. That'll make the derivatives a little bit easier to do. All right, so when we take the derivative of both sides, the derivative of tangent is secant squared, theta d theta, and the derivative of x is dx. Okay, so let's do our substitution. Out front we have a 1/8. We have a dx here, and in place of the dx I'm putting all of this stuff, so it's going to be 2 secant squared theta d theta all over, and on the inside that's going to be tangent squared plus 1. So tangent squared theta plus 1, and of course to the 3/2 power. All right, let's try to clean this up. The 2 and the 1/8 will reduce to give me a 4th secant squared theta all over. What's this going to be? This is going to be secant squared theta to the 3/2 power. Now that's the whole reason I did that, is because I can turn these two pieces into one piece, which means now I can apply that outside power. All right, again, when we do the square root of something squared, we get the absolute value. So this is going to be 1/4 secant squared theta all over the absolute value of secant cubed theta d theta. All right, now notice the 3 stayed as the power. Basically, think about it like this: we had x squared to the 3/2 power, right? Power raised to a power we multiply, 2 times 3/2 is 3. But since you did the square root of something squared, you actually need the absolute value, the cube to be on the inside or the outside. Okay, so I want to get rid of these absolute values because that make my life a lot easier as far as integration goes. So to get rid of these, where would secant be positive? Well, I know that that's supposed to be an S. The secant of theta is really just 1 over the cosine of theta. So secant's positive anywhere that cosine's positive. So if we do the same thing we did last time, this is going to be the secant squared theta over secant cubed theta d theta. I can do that as long as I keep cosine positive, which means it would fall in the first and fourth quadrant. Well, let's reduce a little bit. 1/4, 1 over secant theta d theta, and since we saw just a second ago, secant's 1 over cosine, 1 over secant is cosine. All right, that's an easy enough integral to do. The integral of cosine is sine, so that's the sine of theta plus c. Now again, we didn't start with thetas, we started with x's, and we got to get back. So to get back, you always look at your original substitution to help you get there. Now in our first example, this is our original substitution. Our first example, we could just kind of use that and go directly back, but now I got to get from tangent theta to sine theta. To do that, this is what you're going to have to do with almost every single one of these. From your original substitution, we know that the tangent of theta is x over 2. Build a triangle based off of this substitution. I have a triangle here with an angle theta. I know the tangent is the opposite side over the adjacent side, so this is x and 2. For the third side, use your Pythagorean theorem. This side squared plus this side squared equals this side squared, or just do a little bit of arithmetic, you get x squared plus 4. All right, now here comes a pretty big hint. Once you build your triangle, the third side here should look a heck of a lot like what we started with here. Notice the only difference is the power. Right here, this is the 1/2 power. Over here, this is the 3/2 power, but it's got that same x squared plus 4. If you don't see that, then there's a really good chance that you've made a mistake. All right, so once we built our triangle, now all we have to do is read off what our trig function is. This is 1/4 the sine of theta. According to this triangle, the sine of theta is the opposite over the hypotenuse. So this would be 1/4 the opposite over the hypotenuse plus c. And that's it. There you go. So walk this, we'll do another example or two still, but since we decided that we were going to do a trig substitution and all of our trig identities have 1s, we did a little bit of arithmetic or algebra to get a 1 where the number was. Decided which trig function we wanted to substitute. Make sure you take the derivative. Substituted. Most of the time, not all the time, but most of the time you're going to end up having to restrict your angle to make sure that the trig function is always positive. Integrate whatever's left over and then back substitute. Back substituting generally is going to take you building a triangle based off of the original trig substitution you decided to use. All right, let's try another example. These look really, really complicated because there's a lot of steps to them. But as long as you know how the process works, it's really the same basic steps every time. So let's say if I had the square root of x squared minus 3 all over x. Something like this. All right, you go through all your questions. Can you rewrite it? Can you do a substitution? Will by parts work? Well, you go through all your questions and you say, you know what? None of those really work, and I see I have a function squared and a number with some kind of radical thing involved. That means trig substitution's probably going to be a good choice. Not necessarily, but probably a good choice. Well, to do my trig substitution, I know I need a 1 where the number piece is. So just like before, I'm going to do a couple of steps here. And on the inside of the radical, I'm going to factor out a 3. So that's not the right thing to write. That's going to be x squared over 3 minus 1 all over x dx. So now I can just do the square root of each one of these. Now the square root of 3 is the constant on the top. I'm going to pull that out. And inside the radical, I'm going to write that as x over the square root of 3 squared minus 1 all over x. Now, those two steps of arithmetic or algebra, whatever you want to call it, is really going to make this a little bit easier for you to figure out what substitution to use. So what do we need? We need a function squared minus 1. So we go over here and look at our trig identities. Well, as of the way that they're sitting right now, I do not see a function squared minus 1. Can I manipulate them so I can get that? Well, if I manipulate the first one, I always get 1 minus a function squared, so that's the wrong order. But I notice if I take the second one, that didn't work. If I take the second one and move the second one over, I get that the tangent squared theta is equal to secant squared theta minus 1. There we go, we have a function squared minus 1. So now we know what substitution that we should try. I guess I'll put it up here just for room's sake. So I'm going to use the secant of theta is equal to x over the square root of 3, whatever that function is being squared. Now again, I need to take the derivative of this. So a lot of times it's helpful to isolate the x first. The derivative of secant is secant tangent d theta, and that is just dx. Okay, so here's what we started with. Let's go ahead and there's our square root of 3 on the outside. This is going to be the square root of secant squared minus 1. So square root of secant squared theta minus 1 all over x is, well, from here we can see x is the square root of 3 times the secant of theta, and dx is all of this, square root of 3 secant theta tangent theta d theta. Now this is what's going to happen on a lot of these. So once you do the replacement into the trig functions, you're going to say, there's no way I can do that. I just made the original problem look 1,000 times more difficult by doing that. However, it actually most of the time ends up being a lot easier. So let's see what happens. Numerically, I can see that the square root of 3's cancel. I can see that the secants cancel. So that square root of 3 on the outside stays the same. Inside here, so we canceled out all the denominator, right? We canceled out all that and all that. I can write that as the square root of tangent squared theta times the tangent of theta d theta, or the square root of 3 absolute value tangent theta times the tangent of theta d theta. Well, like always, we're going to have to worry about this absolute value. Where is tangent positively if all students take calculus? Well, it's in the first and third quadrant. So the biggest region I can do without doing two separate regions is just the first quadrant, so from 0 to pi over 2. So we're going to go ahead and write this as, that's going to be the square root of 3 tangent squared theta d theta, as long as our theta falls between 0 and pi over 2, or basically in the first quadrant. All right, how do we integrate tangent squared? Anybody? Anybody? All right, well, can we integrate it directly? Do we know anything that has the derivative of tangent squared? No. But I do know that I could integrate secant, right? Because the derivative of tangent is secant squared. So this is one we may have seen in the past. I can replace tangent squared with secant squared minus 1. So I can rewrite this as secant squared theta minus 1 d theta. Now the reason I want to do that is now I can integrate each one of those pieces, right? The integral of secant squared is tangent, and the integral of 1 is just theta. C, of course. Okay, so we're done-ish, right? We're done integrating, but we do need to back substitute. To back substitute here, we're going to have to do a couple of different things. First off, from our original substitution, I can see the secant of theta is x over the square root of 3. So if I build myself a triangle, let's see, there's theta. Secant's related to cosine, right? Cosine would be the adjacent over the hypotenuse, but this is the flipped over, so this would be the hypotenuse over the adjacent. So that's the hypotenuse over the adjacent. Using your Pythagorean theorem, a squared plus b squared equals c squared, if you solve for this side, you should get that this side is the square root of 3 minus x squared. Oh, sorry, x squared, hypotenuse minus x. X squared minus 3. I did it backwards. All right, so there's our side. So can we figure out what the tangent is here? So here's our square root of 3. The tangent would be what? The opposite over the adjacent. So that would be the square root of x squared minus 3 all over the square root of 3 minus, and how do I get to theta here? Well, theta here, I just have to do the arcsecant of both sides. So this will be the arcsecant of x over the square root of 3 plus c. All right, a little bit more work to do with this one, but same exact concept. Once you recognize the pattern where a trig substitution will work, decide which trig function you want to do all the replacements, and at this step, generally it's going to be really messy, but normally we'll simplify down to something that's much, much easier to do. Once you integrate it, draw yourself a triangle most of the time, and back substitute. All right, let's take a look at maybe one more here. We're running a little long, but that's okay. Let's integrate the square root of, let's keep the numbers easy, 4 minus x squared all over, say, x to the 4th. All right, like always, the directions here would just be integrate. You'd follow all the normal things you would try. You say, oh, look, I got a number and a function squared inside some type of power, which means it fits one of our trig identities most likely. So I'm going to do the 2 steps of arithmetic or algebra I've been doing to make our number a 1. X squared over 4 all over x to the 4th. Then I'm going to do the square root of 4 is 2. I'm going to bring that out. And inside the radical, I'm going to write that as 1 minus x over 4 squared all over x to the 4th dx. Okay, so which trig functions are going to be? I need 1 minus a function squared. So again, as those are sitting up there right now, I don't see 1 minus a function squared. However, if I take the first one, and this is kind of the first way that we did this, if I solve for either sine or cosine, by the way, it doesn't matter which one, generally we solve for sine now. If I solve for sine squared, that would give me 1 minus cosine squared. So if I do that, I get 1 minus cosine squared. So I'm going to let cosine theta equal x over 4. And like I said, it'd work if you did it the other way around and solve for cosine. So that means that 4 cosine theta is equal to x. So taking the derivative of this, I get negative 4 sine theta d theta is equal to dx. All right, let's see what this ends up being. So this is 2 times the integral. Inside our radical, that's going to be the square root of 1 minus cosine squared theta. Down here we have x to the 4th. So this is going to be 4 cosine theta to the 4th. And dx is negative 4 sine theta d theta. All right, let's simplify the numbers. So down here I have 4 to the 4th. That's 4 times 4 times 4 times 4. Well, 3 of them are 64, and another 4 will be 6, 1, 256. So we get 8. So negative 8, and I know this will reduce, over 256. We're going to have the square root of sine squared theta all over cosine to the 4th theta times the sine of theta d theta. Okay. Well, what can we do? Well, I know the square root of the sines. By the way, what would this reduce to? It's negative. Half is 128, half is 64. Is that 32? Check that number. That may not be 32. This is going to give me the absolute value of the sine of theta all over the cosine of the fourth theta times the sine of theta d theta. Now again, I would like to get rid of these absolute values, but we need to make sure that the sign is positive. So we know that all students take calculus. So if I want the sign to be positive, that would be in the first and second quadrants. So this will turn out to be negative 1 over 32, the integral of sine squared theta all over cosine to the fourth theta d theta, but I gotta make sure theta falls in the first or second quadrants. All right, so now we got to integrate this. I'd really like to do a u/du substitution. That won't quite work. That won't quite work, right? I'd probably try letting u be cosine, but du sine squared. I could do something like try to get all this in terms of sines or cosines. That might work. We could try something like this. Let's put a little mark right there because this might not work. Let's see if we try this. I could write sine squared as 1 minus cosine squared all over cosine to the fourth theta d theta. Now, that would be helpful if I took that and broke that into two different ones. Let's see how helpful it'll be. That would be cosine to the fourth theta minus cosine squared theta over cosine to the fourth theta d theta. That's 1 over 32. Integral, let's leave this as 1 over cosine to the fourth theta real quick, but I can rewrite this as 1 over cosine squared theta d theta. All right, so how to integrate this? Well, this one, I'm going to leave this cosine to the fourth here for a second for a very good reason. This I can rewrite as secant squared theta d theta. Now, we just did that a second ago. We can now integrate secant, right? How would we integrate 1 over cosine to the fourth? All right, well, I'm back. Video died again. It's been a lot of fun. But let's take a look at this. Here we were stuck here. We got it to a point where we can integrate secant squared, but we were stuck with 1 over cosine to the fourth. And I think around the last thing I said was, how do we integrate 1 over cosine to the fourth? Now, off the top of my head, I could think of maybe we could do the power reducing formula twice and it'd be a horrible fraction. We'd have to flip it. So off my top of my head, you know, and I don't even know. I don't know. I'd have to mess with that a little bit. Remember, I put some mark way back up here because we just tried turning everything into sines and cosines. We had another choice way back up here. And I think this is the way that it's going to work. What if I were to rewrite this using tangents and secants? Because I saw that sine over cosine. I'm thinking, you know, tangent stuff. What if I were to write this as sine squared theta over cosine squared theta times 1 over cosine squared theta d theta? Now, why would I break it up like that? Well, we've seen in the past we did a lot of integrals with tangents and secants. But what would we have here? We'd have tangent squared theta times secant squared theta d theta. Well, just by rewriting like that, look how easy it became. If we can do a regular u substitution, we let u be the tangent to theta, du is secant squared theta d theta. So this is just negative 1/32. Again, you need to check that number. That would be u squared du. Well, doesn't get any easier than that. So add 1 to the power, divide by the power. So that'd be negative 196 u to the third plus c. Negative 196 tangent cubed theta plus c. Now remember, we didn't start with theta, so we do need to go backwards. So I'm going to actually move this over here at 196 tangent cubed theta. All right, so we got to get back. So our original substitution was using the cosine function. So we've seen this before. Let's draw ourselves a triangle. There's theta. We said that the cosine of theta was x over 4. Cosine is the adjacent over hypotenuse. So this side, let me go a little bit more room. This side will, I made a mistake, everybody watch. This is going to change all the numbers. I'm going to change the original problem to fix this, everybody watch. When I factored out the 4 and I rewrote that should be x over 2 squared. So I'm going to just change this just a little bit. I'm going to change that to a 16, and another factor of 4 out here. So that's not going to change too much. I'm just changing the problem. It was absolutely my mistake. So let's put a 4 right here. And make that a 16. Just fixing all these. Go back, fix it. That's a 16's coming all the way down instead of 30 seconds. That would be a 48. All right. Wow. All right, now, if you want to know how I knew that that was a mistake, it's something that I said at the beginning of the video. By having the 4 there and doing my Pythagorean theorem, it's a squared plus b squared equals c squared. Well, that gave me a 16 minus x squared. And remember, I told you, this piece here better look a heck of a lot like what we started with. But I had a 4 minus x squared, so I knew that I made a mistake. And my mistake was when I went from here, I wrote that as x over 4 squared instead of x over 2 squared. So sorry about the constants, but let's keep going. So according to this, our tangent of theta is the opposite over adjacent. So our final answer is 1 over 48, which I have a feeling has got to be wrong, considering all the numbers I had to fix. Cubed plus c. All right, so ignoring all the small little numerical mistakes that I made in this fun little problem, what did we do? We factored out our number so we could get a 1 so it would fit one of our Pythagorean identities. We decided which Pythagorean identity it fit, plugged that in, found the derivative, plugged all that in. Again, that step generally looks messy. Did all of our stuff to simplify it. This one was a little bit tricky to integrate once we got it completely simplified. Once we decided how to integrate, we back substitute, and again, having to use a triangle here to back substitute most of the time. So trig integrals, they can be fairly long, and just make sure you know where you are in the problem so you don't get lost.